Welcome to Chemistry with Caroline. In this video, we're going to take a look at the reactions of alkenes with carbenes. So let's start with what a carbene intermediate is. This is a carbene. It has two bonds and one lone pair of electrons. So it's neutral, but it's very reactive because it doesn't have a full valence, and it can add to a double bond to create a cyclopropane ring. So we'll go to the next slide to look at some specific reactions. So carbenes are really reactive, and there's not an easy way to store a carbene. You usually have to generate them in situ, so make them in solution. So one way to do that is to take a molecule that has a bunch of electronegative groups on it, and therefore this proton here is going to be sort of acidic. All those bromines are pulling electron density away from that proton and weakening the bond. So if we put a strong base in solution, we can just have an acid-base reaction where we deprotonate that molecule. And that will give us initially a carbanion. So right now this carbon has a lone pair and 3 bonds. That means it's negatively charged. And this intermediate is called a carbanion. And then of course you'd also have water as your conjugate acid from the hydroxide base that you used. Then, because of all this electron density in close proximity, that bromine can leave, and that will generate the carbene intermediate that we would use for addition across a double bond. So here I've redrawn our carbene intermediate. This is dibromocarbene, and I'm going to add it to a cyclopentene, and it's going to be that pi bond that's going to react. This is a concerted reaction. So the lone pair on the carbene is going to attack one of the carbons, and then the pi bond is going to come make a new bond to the carbon to complete that octet. And that will give me this compound. And when I add that ring, it's going to have stereochemistry associated with it, but both planes of the alkene look the same. So there's an equal amount of the carbene that adds to the top face as there is carbene that adds to the bottom face. And that's because there's no substituents coming off the cyclopentene ring. So the other way that you can draw this is to just draw lines, because when you draw lines, you're saying this molecule is not chiral. It's an achiral solution that's been formed. It's a racemic mixture, 50-50 on the top and the bottom. So there's 50% addition to the top and 50% addition to the bottom. So you either have to draw both of these two enantiomers and note their relative 50-50 abundance, or you can just draw the molecule like this, where you don't include stereochemistry, and by drawing it like that, you're indicating that it's not a stereospecific reaction in this case, because the carbene can add to the top face or the bottom face equally. So I want to show you another example where we start with an alkene that has a particular stereochemistry associated with it. So you can see here that the ethyl group and the methyl group are opposite one another in this alkene. That would be the E stereoisomer. And then here, the methyl group and the ethyl group are on the same side. And so that would be the Z stereoisomer. So because this is a concerted reaction, whatever stereochemistry the alkene has is the same stereochemistry that will be observed in the cyclopropane ring that is formed, because the ring has no free rotation and the alkene has no free rotation. So in one step, the carbene is going to add to one carbon as the pi bond comes around and makes a new bond to the carbene carbon. And so that gives me, I'm going to draw the cyclopropane ring that we form, and you will only see product where the methyl and the ethyl are opposite one another still. So they were opposite one another on the double bond, and they are opposite one another on the cyclopropane ring that's formed. So if the methyl is forward, the ethyl is back, and vice versa. So it could also form the enantiomer to this, where methyl's back and ethyl's forward, but none of them would be on the same side. If we look at the bottom example here, same mechanism, and the stereochemistry will again be retained, so you would only see formation where the methyl group and the ethyl group are on the same side. So they will either both be wedges, or in the enantiomer, they would both be dashes. So this reaction is stereospecific with respect to the alkene that is forming, because whatever the stereochemistry of the alkene is will be the same stereochemistry for the formed cyclopropane ring. So I want to show you one more example here, and this doesn't have a free carbene as an intermediate, but what we would call a carbenoid over here. So you start out with a CH2X2 derivative, often I2, because that's a long, weak bond. It's easy to break. This is in the presence of a zinc and a copper co-catalyst, and the zinc is actually going to insert itself between the carbon-iodine bond. And that's very common, actually, in carbon chemistry. Metals are able to insert between a CX type bond. And we haven't probably seen any examples at this point in OChem, but we're going to see several when we get to OChem 2 in second semester. And so this intermediate, this carbenoid intermediate, behaves sort of like a carbene, and it can also add across a double bond. So we'll go to the next slide, and I'll show you the mechanism for that. Okay, so here I've drawn my carbenoid intermediate. It's more stable because it has a full octet, so it's just a little bit easier to handle. And I've got an alkene here, and this alkene has a substituent on it, which means that the two faces of the cyclohexene are not the same. The top face has an ethyl sticking up, and the bottom face doesn't. Okay, so you actually are going to see selectivity here. You'll see a major and a minor product because of steric hindrance that would occur because of that substituent. So let's take a look at the mechanism. The zinc iodine is going to just dissociate, and so these electrons between the carbon and the zinc are going to come over and attack that carbon, much like the carbene lone pair would. The pi bond then is going to come over and attack the carbon there, and that will kick off iodine as a leaving group, so we don't exceed the octet rule. So the major product is going to be the product in which the carbon adds opposite of the ethyl group because it's bulky, right? And so it's going to be kind of blocking that face. And so this is staying the same. Nothing happened to that, but my CH2 that I'm adding is going to be opposite of that in my major product because it's not going to have as much steric hindrance as it adds. The minor product then would be where those are on the same face. So the CH2 group would have added to the same side, and it would have experienced more steric hindrance because of that ethyl group there. Now the stereochemical relationship between these two is diastereomers, right? Because the ethyl group remains a wedge. Nothing happened to that, so that stereocenter is the same. And then the stereocenter where I formed the cyclopropane ring is different, right? Here you have dashes, and here you have wedges. And then if we're thinking about what it is we added, right, the zinc iodine is going to dissociate. I don't have to draw anything to show that because the electrons are what I show moving with arrows. And so those are moving to the carbon. Zinc iodine is now floating around in solution like this. And then the other iodine left. So what you added was this CH2, and that's what we see as the addition product in our final products. So this has been a look at the addition of carbenes and carbenoids to alkenes to form cyclopropane derivatives and some of the stereochemistry and selectivity that are present in those reactions. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.